Let's continue our talk today and continue actually this series of steady flow devices. And today, inshallah, we'll be starting with the throttling valve. So the third set of devices actually is the throttling valve. Actually, throttling valve is a very important device which is used actually mainly in refrigeration and air conditioning system. The idea of the throttling valve is that it's a kind of flow restriction that result actually in significant drop in pressure and also significant drop in temperature. So the idea of the throttling valve or adjustable valve is that we have a valve in the flow direction. The flow is going, let's say actually we have flow inside the tube or something. This flow actually is restricted to a very small area under this valve. So in this case, the area is reduced. So area is reduced, too much reduction, too much restriction. So in this case, the velocity of the flow will be increased and the pressure actually will get down. Pressure will get down based on Euler equation of velocity increase, the pressure will get down, and also here the flow is restricted in very small area, so the friction will be too high. So the flow will actually lose its pressure while crossing this throttling valve. But after passing and after leaving this throttling valve, the flow actually will retain the same area, the same pipe area, and it will retain its velocity back. But actually the pressure has dropped down and also the temperature has dropped down of the flow. And this is the main function of the throttling valve, is to have actually significant reduction in pressure and also significant reduction in temperature in this case. The main application in this case is in the refrigeration cycle. If you look at the refrigeration cycle, we have this is a kind of the evaporator, which is the freezer or the food compartment, which is actually the simple example like the fridge at your house. If you look at it, there is an evaporator. This evaporator in which actually we have the food compartment or the freezer who put actually the food in this case. So usually freon, we have considered subjected to one freon, which is 134A. So let's assume this freon is being passed through the circuit. So in this case, this freon is coming to the evaporator or the freezer of your fridge in the liquid form. So it is coming in the liquid form. Usually its temperature is about minus 25 degrees C or something. You can look here, this is some numbers you can look at. This is the evaporator, the flow is coming at minus 25 degrees C and 120 kilopascal in this case. Coming to the evaporator, so what happened inside the evaporator or the freezer? In this case, the freon is coming at low temperature, so it will absorb heat from the food compartment. This absorbed heat, we call it actually Q low. Q low, why Q low? We call it Q low because heat is added to the refrigerant under low temperature. The temperature here in this case is very low. So the freon absorbs the heat from the food compartment and it was in the liquid form. Then it is actually converted to the vapor phase. Okay, usually under the same temperature. So this heat actually is latent heat. It will convert the phase from the liquid phase to the vapor phase in this case. Now this vapor actually is being passed through a compressor. So we have compressor in the fridge. This compressor is connected to an electric motor to drive the compressor so that it can compress actually the freon inside this side. And the electric motor is connected to an electric socket, so it consumes actually electrical power, and that's why the fridge is consuming electrical power. Electrical power to run the electric motor is running actually this compressor. So what will happen inside the compressor? The function of the compressor, it will raise the pressure of this vapor and also its temperature will be raised in this case. If you look at this example in the slide, the temperature will be raised to about 60 degrees C and the pressure will be raised to about 800 kilopascal. Now we have freon in the vapor phase at high pressure and high temperature. But we need to repeat the cycle again. We need to cool down this refrigerant so that we can pass it again inside the food compartment to absorb heat. Then in this case, if you look at the back of the fridge, you will find there is a net of wire. Net of wire actually, this is net of hot wire. You will find it always hot. This is actually net of hot wire is called the condenser. We just pass the freon inside those tubes, and then actually this freon is rejecting its heat. This freon at high temperature, so we call it actually Q high. This Q high is the heat rejected from the Freon to the surrounding air, like the kitchen air or something. Like it will reject this heat inside this condenser to the surrounding air. Now it will be converted from the vapor phase to the liquid phase, but still actually it is at high pressure and also still it is at high temperature. Like if I pass this Freon, liquid Freon, I convert it from the vapor to liquid. It is liquid now, but liquid under high pressure and high temperature. If I pass that again inside the evaporator, it will heat up the system, not cool it down. So what should we do in this case? In this case, we have what we call actually the expansion valve. Expansion valve or capillary tube. We call it also as capillary tube. If you look at actually also at the back, you will find there is actually a tube with very small diameter. Long tube with very small diameter. So the idea here is what? To have a small area for the flow, restrict the area of the flow. Then in this case we will have pressure drop, and in this case the temperature will get down. We call this tube capillary tube in the refrigeration system, which is used there, or we call it actually as expansion valve. So in this case, the Freon, in this case will have, it is in the liquid phase. It will remain actually as liquid phase, but we will have actually significant drop in pressure and significant drop in temperature inside this expansion valve. Now we get back again to the same initial point, to the liquid state under low temperature in this case. Now we can actually repeat this cycle again. This Freon can absorb heat from the food compartment inside the evaporator or the freezer. Then it can convert to vapor, and then actually we can repeat this cycle again. And this is actually what we call the refrigeration cycle. Refrigeration cycle is used actually in the refrigeration system, and also it is used in the air conditioning system. Okay, so in the air conditioning system, instead of cooling down a food compartment, in this case we are cooling down actually the surrounding air. So we come up with air. This air is passed inside actually this evaporator. It will cool down. Then we can take this air to actually a given room to cool it down through air conditioning system. So the same cycle is applied in case of refrigeration system, like the fridge at your house, and also in the air conditioning system also we have the same cycle, typically the same cycle. But in the fridge we are cooling down the food compartment. In the air conditioning system, which you have, if you have a split unit or something on the wall, it has also an evaporation cycle. A refrigeration cycle. In the refrigeration cycle, in this case, we cool down the air instead of the food compartment in this case. Let's apply the first law of thermodynamics for this case. If we have a throttling valve. First of all, it is called the throttling valve. It is called also as adjustable valve. That is valve that can be adjusted. Its opening can be adjusted. It is called also as capillary tube or expansion valve. All of these means actually that we have a throttling valve. Also in case when we have porous plug or porous media. Porous media is a media actually with very small opening, so that actually the flow can go through this very small opening. Then in this case the area is restricted, so the pressure will get down in this case. So if we told you we have porous plug, porous plate, porous media, expansion valve, capillary tube, all of this means that we have a throttling valve in this case. And the idea of the throttling valve is to make restriction of the flow area. Then in this case we can have a drop in pressure and significant drop in temperature. And the main application actually is in the refrigeration cycle. Okay, but let's look here at this valve and apply the first law of thermodynamics or a steady flow. This is a steady flow open system device of single stream, and also let's apply the mass equation as it is open system. So for the mass equation, this is steady flow single stream. So m dot is constant at any cross section. So let's say before this valve, this cross section 1, the inlet, and after the valve, this is cross section 2. So we can say m dot 1 is the same as m dot 2. We call it m dot in general. So in this case, the m dot will equal to density rho 1 a1 v1, same as at the outlet section rho 2 A2 multiplied by the velocity V2. Okay. But this is the mass equation. Let's apply the energy equation or the first law of thermodynamics for a steady flow device, open system of single stream. It will be Q dot minus work dot equal to M dot multiplied by delta H plus a change in kinetic energy plus a change in potential energy. Usually at cross section 1 and 2, we have the same elevation. Z1 is the same as Z2. We have the same elevation. So in this case, this term is a change in potential energy is 0. Usually the flow, before coming to the throttling valve, it's a velocity, let's say V1. The velocity here is increased in this restriction. Just below this valve, the area is restricted, so the velocity is increased. But when the flow retain back the same cross-sectional area, get back to the normal cross-sectional area of the tube at the exit section, section number 2, in this case, for the same cross-sectional area, almost we can retain the same velocity. So we can say also V1 will be almost the same as V2. We have the velocity is increased, but just below this valve. But after the valve, the flow will retain the same normal area of the tube. Then in this case, it should have very similar velocity in this case. So usually V1 is the same as V2. So the change in kinetic energy will also be 0. But in this case, this is very small dimension valve. So in this case, we don't have heat transfer. So in this case, heat is equal to 0. And in this case, we don't have any kind of work, just it is flow. So heat work also is equal to 0. So now we are left with what? In this case, the change of enthalpy through the throttling valve will equal to 0, or we can say H1 will be the same as H2. So if we have a throttling valve, this is actually, if we told you in any application we have a throttling valve, that means actually that the enthalpy is constant across this throttling valve. So H2 is the same as H1, and the enthalpy is equal to internal energy plus flow energy. So U1 plus V1 will equal to U2 plus V2 multiplied by specific volume V2 in this case. So if we told you actually in any applications that we have a throttling valve, that means actually the enthalpy of the flow before this throttling valve is equal to the enthalpy of the flow after this throttling valve. So the enthalpy remains constant when the flow is crossing actually a throttling valve in this case. Now in case when we have ideal gas. Ideal gas, we said enthalpy, we can define enthalpy as Cv as function of temperature multiplied by dT, or delta H is equal to Cv dT. So that means actually in case of ideal gas, enthalpy is only function of the temperature. This is actually in case of only ideal gas, because we said in case of ideal gas, we can treat any gas as an ideal gas under very low pressure. And in this case, we can define the enthalpy only as function of temperature. Delta H is equal to Cv, which is function of temperature only, dt. Okay. But for a throttling valve, if we have an ideal gas is being passed actually through a throttling valve, in this case, enthalpy should be constant. But enthalpy is only function of temperature for ideal gas. That means in case of ideal gas, also the temperature will be remaining constant in this case. Okay. So the main idea of the expansion valve or the throttling valve to have drop in pressure and to have drop in temperature. Okay, but this is in case of what? In case of liquids in this case. But if you have a gas and you said I will be using throttling valve to reduce the temperature of this gas, if the pressure is low, actually the temperature of the gas will not be changed. It will result actually in the same temperature. Okay. So let's have an example, solve an example to see. Here in this example, he said we have refrigerant 134A. So refrigerant 134A. So this is you have the working fluid in this case. Enters a capillary tube. So he said we have a capillary tube. Capillary tube means actually we have a throttling valve. This is a kind of throttling valve. Enter a refrigeration system as saturated liquid at pressure equal to 0.8 megapascal. So this is the throttling valve coming into, let's say, at cross section 1 with pressure B1 is equal to 0.8 megapascal. and it is saturated liquid. Saturated liquid, that means X1 is equal to 0. And after leaving actually this throttling valve, the pressure at section 2, B2 is equal to 1.2 megapascal in this case, 0.12 megapascal. As the pressure should drop down in this case. After the throttling valve was 0.8 megapascal, it will drop down to 0.12 megapascal in this case. And we need to calculate the final quality of the mixture of the, in this case, he assumes that we should have a saturated mixture of refrigerant after passing this throttling valve. We need to calculate the quality X2, and we need to calculate the difference in temperature delta T before and after this throttling valve. Okay. طيب when you say شباب capillary tube, adjustable valve, throttling valve, expansion valve, all of these that mean actually we have a kind of throttling in this case. That means the enthalpy will be remaining constant in this case. But what we say actually H2 will equal to H1, and this is based actually on the first law equation. Right, let's solve this problem. We have first of all B1 is equal to 0.8 megapascal, and we have X1 is equal to 0, or saturated liquid. Saturated liquid, that means actually we can use the saturation table, but this is a shabab refrigerant, so I will be using table from A11 to A13. Here the pressure is given and the state is saturated liquid, so in this case I will go to table A12, A11 for temperature, A12 was this pressure, then in this case the temperature T1 will equal to the saturation temperature in this case. If you look at this temperature, it equal to 31.31 degrees C in this case, as it is actually saturated liquid. And as it is saturated liquid, we can get the enthalpy H1 will equal to H fluid in this case. H fluid at this point in pressure of 0.8 megapascal will equal to 95.47 kilojoule per kilogram. Okay. So this is at state number 1. At state number 2, we have pressure B2 equal to 0.12 megapascal, and we have in this case the second property that we need. Based on this, actually a kind of throttling, flow throttling, so enthalpy H2 will be the same as H1. So in this case, H2 will equal to H1. Now we have the pressure, and we have one specific. So in this case, I will take this pressure for refrigeration. I will go to table A12, and in this case, I will get the value of H fluid, and also get the value of H gas, and compare it actually with the given value, which we have just calculated -5. In this case, you will find H2 is greater than H fluid and less than H gas, so the state actually is saturated mixture. And when we have saturated mixture, in this case the temperature T2 will equal to the saturation temperature at this pressure, which we can get from this table. At this pressure, the saturation temperature will equal to -22.32 degrees, and this is the final temperature T2. So we need to calculate the quality. We have the enthalpy H2, and we got H fluid and H gas from the table. Then in this case, we can get H2 will equal to H fluid plus X2 multiplied by H gas minus H fluid, which is HFG. This we have H2 equal to H1 95 point something, and we got H fluid and H gas. Then we can calculate X2. X2 will equal to 0.34 in this case. Right? Here, Shabab, also we need to calculate delta T. So delta T will equal to what? T2 minus T1. T2 is equal to what? Minus 22.32. This is T2 minus T1. T1 is 31.31. Okay, so it will negative. So it will equal to minus a kind of minus 53.6 degrees. Okay, sure. So don't take the absolute value. So T2 is negative minus T1, which is positive. So in this case, it will negative plus negative. So in this case, delta T will be negative in this case, which is the total. You don't just take the difference of the absolute values. Okay. طيب by this we are done with the throttling valve. So let's move to another device, steady flow device, which is the mixing chamber. Mixing chamber, if you have, is a common example for steady flow devices. In this case, actually, the common example is like the shower at your home. In the shower, actually, we mix actually cold fluid plus hot fluid, and at the end, actually, we can get a third stream actually leaving this shower mixer at a moderate temperature. Okay, so if you have a hot fluid, here is an example. We have hot fluid is being mixed with a cold fluid, then we can have actually a stream at intermediate temperature in this case. Also, the mixing chamber have another application to mix different gases of different concentration. Then at the end, actually, we can have a homogeneous mixture at the outlet section of this mixing chamber. So mixing chamber, we mix two fluids of different temperature. Then in this case, we can have only one stream leaving this system. And also we may have more than one stream at the outlet section, whatever. So let's consider in general when we have a mixing chamber. So let's say here we have a mixing chamber. Like as we said, the shower. So let's consider this is actually a very simple example. Like the shower, we have hot fluid. So let's say hot fluid is coming at cross section number 1. This hot fluid is being mixed actually with a cold fluid. Cold one, let's say coming at section number 2. Both of them are actually mixed inside this mixing chamber. This is hot fluid is coming, let's say, at temperature T1, and this one is coming at T2. T2 is less than T1. Then in this case, they can heat up the cold fluid, and then we can have actually a mixture leaving, let's say, at state number 3. In this case, the temperature T3 should be greater than T2, which is the temperature of the cold fluid, and it should be less than actually the temperature of the hot fluid in this case. Okay. Right, let's look at actually this mixing chamber, and let's draw a control volume. This is the control volume of the system we are going to study, and look at the control surface of this control volume, and look at the masses and the energies that are actually crossing this control surface. And let's apply first of all the mass equation. So this is actually a steady flow device, but we have in this case more than one inlet in this case. So in this case, we can say summation. In this case, we have to add the summation sign. Summation of M dot inlet will equal to summation of M dot exit in this case. So we say that in case we have more than one inlet or more than one outlet, then in this case we can add the summation sign to the mass equation. Type, what kind of inlet we have in this case? So we have hot fluid 1 and the cold fluid at 2. Then we can say M dot 1 plus M dot 2. This should equal to the summation of the mass flow rate at outlet section. We have only one outlet at cross section through, so this will equal to M dot 3. If we have a let's say this is a kind of example when we have only two inlet and one outlet in this case. But the rule is general. If we have, let's say, M dot 3 is coming in, M dot 4 is coming in, and we have here actually leaving, we have 5, and we have leaving 6, whatever. So we can just add them up here. So it will be M dot 1 plus M dot 2 plus M dot 3 plus M dot 4 equal to M dot 5 plus M dot 6, all of the leaving system. So the summation of mass flow rate inlet is equal to the summation of mass flow rate outlet in this case, whatever the number of inlet and whatever the number of outlet in this case. And let's apply the energy equation. So the energy equation in this case, when we have more than one inlet or more than one outlet, so it will equal to Q dot minus work dot will equal to. In this case, if we have more than one inlet or more than one outlet, we have to add the summation sign. It equal to summation of M dot exit multiplied by H exit plus V exit squared divided by 2 plus G multiplied by Z exit minus summation of M dot inlet multiplied by H inlet plus V inlet squared divided by 2 plus G multiplied by Z inlet in this case. Okay. Right, let's look at this mixing chamber. In this case, if we have hot fluid being mixed with a cold fluid, In this case, actually, the heat will transfer from the hot fluid to the cold fluid, but internally or inside actually the mixing chamber. But if you look externally for this control volume, in this case, actually, we don't have heat transfer to the surrounding medium in this case, or the system in this case is not associated actually with heat transfer to the surrounding air. So the system is almost adiabatic in this case. So the heat transfer in this case is equal to 0. And also in this case, we have just the flow. We don't have any kind of work. So in this case, the work also is equal to 0. Usually the inlet section area and the outlet section area are very identical. Or if there are actually change or something, it will be just insignificant change. So that means actually we cannot get any much change in the velocity from the inlet to the outlet section. So we can just neglect the change of kinetic energy. The change in potential energy, usually we have the same elevation, so we don't have a change in potential energy in this case. So the equation will be left with summation of M dot exit multiplied by H exit will equal to the same as the inlet section, summation of M dot inlet multiplied by H inlet in this case. Or we can say summation of M dot exit, H exit will equal to summation of M dot inlet multiplied by H inlet in this case. Now let's apply this here. We have two inlet and one outlet in this case. So we can say M dot 1 H1 plus M dot 2 multiplied by the enthalpy at cross section number 2. In this case, if it is water or something, then we can give you the pressure and temperature of water at cross section 1 and cross section 2. Then we can calculate H1 and H2. I can give also the mass M dot 1 and M dot 2. Then we can apply the mass equation. Then we can calculate M dot 3 in this case. Right, this is actually the energy equation. M dot 1 H1 plus M dot 2 H2 will equal to M dot H exit, which is M dot 3 multiplied by H3 in this case. Now if we have another exit, then in this case I will add plus M dot 4 H4, whatever. So we have summation of mass flow rate exit, H exit is equal to summation of mass flow rate inlet multiplied by H inlet in this case. And this is the mass equation in case when we have mixing chamber, when we are mixing actually two fluid streams of different temperature and different pressure to have one outlet stream. Then in this case we can say summation of mass flow rate inlet will equal to summation of mass flow rate outlet, and the energy equation will be reduced to summation of mass flow rate exit H exit will equal to the summation of mass flow rate inlet multiplied by Hn. In the mixing chamber, heat is transferred from the hot stream to the cold stream, but internally. We don't have external heat transfer in this case. Okay. So we have another steady flow device which is very similar to the mixing chamber, but in this case the two fluid does not mix. We have only heat transfer in this case, and that's why they are called actually as heat exchanger. So I think this is the fifth set of steady flow device when we have actually heat exchanger. Heat exchanger, the idea of the heat exchanger is that we have also two fluid, hot fluid and the cold fluid, but the two fluid does not mix. Just we have actually heat transfer from the hot fluid to the cold fluid. And this is the idea, Shabab, of the condenser. The idea of the condenser is to pass actually cold fluid to absorb the heat actually from the hot fluid in this case, to cool down the hot fluid. So if you look at the heat exchanger, so let's say this is actually a heat exchanger. So it exchanges the heat from the hot fluid between the hot fluid and the cold fluid. So let's consider a simple example when we have hot fluid. So usually we cross the hot fluid inside the tube. So we have hot fluid here. It's coming, let's say, at cross section number 1, and it is passed inside actually this tube here, and it is leaving at cross section number 2. Okay, here actually we pass the cold fluid. So usually cold fluid is provided from the bottom, so that actually when it is leaving at the top, it should actually went through actually the whole body actually of the hot fluid. But if you drop the cold fluid from up there, It may have a short circuit directly. It will not go through actually the whole tube outside around this tube. It may have short circuit directly, and it may just leave from down there without actually absorbing the heat. So usually if we have cold fluid, we pass actually the cold fluid from the bottom so that actually it will fill the whole tank before actually leaving. Now it is able to absorb the heat from actually the hot fluid in this case. So heat is transferred from the hot fluid to the cold fluid. But again, this heat transfer is internal heat transfer within the system. But externally, we may not have actually heat transfer in this case. So the cold fluid is coming, let's say, at cross section number 3 and leaving at cross section number 4 in this case. So we have two fluids, one hot fluid and one cold fluid. They does not mix actually, but they exchange the heat. So heat is transferred internally from the hot fluid to the cold fluid in this case. Right, let's apply the mass equation. If we apply the mass equation, in this case, we have more than one inlet, hot fluid, and we have cold fluid inlet. We have hot fluid out, we have cold fluid out. We have more than one inlet and more than one outlet. We have to add the summation sign in this case. So the summation of M dot inlet will equal to the summation of M dot exit. Now, what are the inlet here? We have inlet of hot fluid at cross section 1 and the inlet of cold fluid at cross section 3. So we can say M dot 1 plus M dot 3. That should equal to actually M dot 2 plus M dot 4 in this case. But we have for the hot fluid, M dot 1 is the same as M dot 2. And for the cold fluid, M dot 3 is the same as M dot 4. We call it actually M dot cold in this case. So M dot 1 is the same as M dot 2. We call it actually as M dot hot. So M dot 1 is the same as M dot 2, which we call it actually as M dot the mass flow rate of the hot fluid. And we have also M dot 3 is the same as M dot 4. We call it actually M dot C, which is the mass flow rate of the cold fluid in this case. And this is the general equation. Okay, M dot 1 plus 2 equal to 3 plus 4 in this case. Let's apply the energy equation or the first law of thermodynamics for this system. So we can say Q dot minus work dot, as we have more than one outlet, so it will equal to summation of M dot exit, H exit plus V exit squared divided by 2 plus GZ exit minus summation of M dot inlet, H inlet plus V inlet squared divided by 2 plus G multiplied by Z. Okay, and let's look at the energies crossing this system. First of all, in this case, we have heat transfer, but internal heat transfer from the hot fluid to the cold fluid. But externally, we don't have heat transfer in this case. This flow also, this is just a flow. We don't have work in this case, so we don't have work also as well in this case. So the heat transfer in this equation is 0. Work is equal to 0. Usually, we don't have a change in cross-sectional area, so we will not have significant change in velocity from the inlet to the outlet, and also the elevation can be neglected. Then we can come up actually that summation of M dot exit, H exit, will equal to summation of M dot inlet, H inlet, similar to the mixing chamber. So summation of M dot exit, H exit will equal to summation of M dot inlet multiplied by the enthalpy H inlet. Or we can say from this case, M dot 1, H1, this is inlet number 1, plus inlet 3 for the cold water, M dot 3, H3. That should equal to M dot exit. We have 2 of the hot fluid, M dot 2, H2, plus 4 for the cold fluid, M dot 4 multiplied by H4 in this case. Okay? But from the mass equation, M dot 1 is the same as M dot 2. We call it actually M dot hot, the mass flow rate of the hot fluid. And M dot 3 is the same as M dot 4. We call it as actually M dot cold. So based on this equation, we can come up here actually that the mass flow rate of the hot fluid multiplied by M dot hot multiplied by H1 minus H2 This should equal to mass flow rate of the cold fluid, which is m dot 4, is the same as m dot 3, multiplied by h4 minus h3. And this is the equation for actually a heat exchanger. So we can say summation of m dot inlet h inlet will equal to summation of m dot exit h exit, or m dot 1 h1 plus m dot 3 h3 will equal to m dot 2 h2 plus m dot 4 multiplied by h4. M dot 1 is the same as m dot 2, we call it m dot hot. And m dot 3 is the same as m dot 4, we call it m dot cold. Then in this case we can take them as common. Then we can say m dot hot multiplied by h1 minus h2 will equal to m dot cold multiplied by h4 minus h3. In this case, if we should give you the properties of the hot fluid at point 1, let's say water, pressure B1 and temperature T1, then we can calculate the enthalpy H1. And let's say here actually for the cold fluid, let's say we have a refrigerant or something. So usually refrigerant is the hot fluid and we need it to cool it down with water. So let's say we have refrigerant here, hot refrigerant at pressure and temperature at point 1. Then we can use the refrigeration table to calculate the enthalpy H1 and also the enthalpy H2. If we have water here at cross section number 3, it will be given the pressure and temperature. Then we can calculate H3 and also we can calculate H4. Then we can substitute here. Then we can calculate actually either the mass flow rate of hot fluid or the mass flow rate of the cold fluid, the mass flow rate required actually to cool down this hot fluid in this case. Type, this is all what we want to say, but there is a tick here. What if we have, here we said we don't have external heat transfer. The system is almost adiabatic, externally. And this term in the equation is 0. But what if he said actually we have a kind of heat loss to the surrounding medium in this case? So in this case, just I will add here plus Q dot external. Okay. So if we have external heat loss to the surrounding, just I will add it actually to this equation that we have developed here, which will be here. It will be Q dot external plus m dot hot multiplied by delta H will equal to m dot cold multiplied by delta H. So if we have external heat transfer, maybe it will come to your exam, not adiabatic. So in this case, we have to add here Q dot external to this equation. So it will be Q dot external plus m dot hot, H hot multiplied by delta H. This should equal to m dot cold multiplied by delta H in this case. Okay. But if I need to calculate, we assume this system is adiabatic and we don't have external heat transfer. But we have internal heat transfer from the hot fluid to the cold fluid. If he asked you, or I need to calculate actually the heat transfer from the hot fluid to the cold fluid, the internal heat transfer in this case. So in this case here, we have to study only the hot fluid in this case. So I will be considering this will be my control volume. I will just draw it around actually the hot tube. And in this case, we have single stream coming at section 1 and leaving at section 2. And in this case, we have heat is transferred from the hot fluid to the cold fluid. So let's apply the first law of thermodynamics for the hot fluid. So for the hot fluid, considering the hot fluid only inside this tube. So in this case, the mass equation is m dot 1 is the same as m dot 2, single stream in this case. Apply the first law of thermodynamics, Q dot minus work dot, m dot plus delta H plus a change in kinetic energy plus a change in potential energy. In this case, we have heat transfer, but do we have work? No, we don't have work. And usually we neglect the change in kinetic and the potential energy in this case. Then in this case, Q dot lost from the hot fluid will equal to m dot hot multiplied by the change of enthalpy, which is H2 minus H1 in this case. So the heat transfer from the hot fluid to the cold equal to m dot hot multiplied by H2 minus H1. But what about the heat absorbed by the cold fluid? We can also study the cold fluid alone, and in this case, Q dot cold will equal to the same mass flow rate of the cold fluid multiplied by the difference in enthalpy H4 minus H3. And based on the equations that we have developed here, this is M dot hot, H difference in enthalpy of the hot fluid H1 minus H2 will equal to M dot cold multiplied by H4 minus H3. And this is what we call what? This is Q dot hot, which is this one. This term, Q hot M dot hot H2 multiplied by delta H. And this is actually Q dot cold. It will be the right hand side term of the equations that we have developed. So for a heat exchanger, Q dot hot should equal to Q dot cold based on the equations that we have developed. Unless what? Unless we have external heat transfer. If we have external heat transfer, not adiabatic, then in this case we should add it to this equation. Okay? So it will be Q dot external plus M dot hot multiplied by H1 minus H2 equal to M dot cold multiplied by H4 minus H3. If the system is adiabatic, the heat exchanger is adiabatic, then Q dot hot will equal to Q dot cold in this case. Okay?